Welcome. In this worked example, we'll be going through question 1 from paper 42 that was administered in October, November of 2019. Paper 42. State Newton's law of gravitation. Here I am without a writing tool. Pen. Not just any pen will do for this paper. It has to be an epic pen. All right, so Newton's law of gravitation, we could think about it just in terms of, well, that's pretty touchy now. G M M over R squared. All right. That doesn't really state Newton's law of gravitation. That's sort of the equation form, but if it helps us to say the force of gravity is directly proportional to the product of the masses and inversely proportional to the square of their separation distance. You could state all that in words. That's sort of what's captured in this equation. It says, the astronomer Johannes Kepler showed that the period t of rotation of a planet about the sun is related to its mean distance r from the center of the sun by the expression here, where k is a constant. Use Newton's law to show that for planets in circular orbits about the sun of mass m, the constant k is given by this, where g is the gravitational constant. Explain your work. All right, scroll down a bit here. All right, so we have to state Newton's law, and now we're going to use this law to show that this constant k, sort of Kepler realized this, there's a relationship between these things, there's some constant here. And Newton said it's equal to this, gm over 4 pi squared. All right. Circular orbits, okay, so keep that in mind, that's something that we really emphasize here. So for something to move in a circle, it has to be pushed towards the center of the circle. That's called a centripetal force, and we know that that centripetal force is equal to mv squared over r. So we can say mv squared over r is the center seeking or centripetal force provided by gravity, which is g m m over r squared. Equating these, you get mv squared over r equal to g m m over r squared. Cancel one of those with that. Cancel this m with that. And we've got v squared equals gm over r. We know that velocity is 2 pi r over t, right? Because it's a circular motion. So a circle has a distance around it equal to 2 pi r, where r is the radius of that circle. So the distance around the circle, 2 pi r, and it goes over time t. As we said on the chalkboard, substituting that in for v, we get 4 pi squared r squared over t squared equal to gm over r. And remember, we're trying to show that there is this constant that's equal to r cubed over t squared. So let's try to sort of put that all on one side of it. So if we multiply both sides of this by r, then that becomes r cubed over there. Get rid of this one. And now we've got in pink ink 4 pi squared. Let's see that okay? Yes, it's not too bad. 4 pi squared r cubed over t squared equal to gm. And we want to get, there's some constant k equal to r cubed over t squared. Well, there's r cubed over t squared. So let's just, sort of isolate those and divide each side by 4 pi squared. So we're doing it to that side. Algebra says you got to do it over here. Get rid of those 4s, get rid of those pi squareds, and we've got r cubed over t squared equal to gm over 4 pi squared. And now we've shown that this constant k, right, which is equal to r cubed over t squared, is gm over 4 pi squared. So that agrees with that, right? That's how we do it. Now let's put this physics to good use here. We've got a satellite in a circular orbit about Mars. The radius of the satellite is 4.38 by 10 to the 6 meters. The orbital period is 2.44 hours. Easy come, easy go. Don't worry, you can just pause the video and rewind it if you still needed any of that. So now we're going to calculate a value for the mass of Mars. So we said that k was r cubed over t squared. And it's equal to gm over 4 pi squared. I'll derive all that again. R cubed over t squared is gm over 4 pi squared. Right? So that's why k is equal to this. But we want to know m, the mass of the thing being orbited, the mass of Mars. So let's make that the subject. In order to do that, I want to get rid of all this stuff on this side. So if I divide by g divided by g is 1. 1 times the rest is the rest. I multiply by 4 pi squared. So this is a nice convenient factor to multiply the right side of the equation by. And the nice thing about algebra is I'm allowed to do that as long as I keep track of it and do it to the other side. So if I multiply this side by 4 pi squared over g, it effectively cancels out everything I don't need over here. So I've isolated the thing I want to know, the mass, and now I've got what it's all equal to over here. If you look at the chalkboard, you can see, oh yeah, there it is there for me. Moreover, on the whiteboard, I've shown you that g has base units of meters cubed per kilogram second squared. So r has to be in meters, and that's kind of nice because it already is. But t has to be in seconds. Okay, the units of g are in seconds squared. And so I really try to sort of emphasize that before we began, so that you don't just sort of plugged in 2.44 here. We have to plug in what? So let's take care of this right now. 2.44 hours, and there are 24 hours. Wait, we don't want to go to days, we want to go to seconds. So we want to say that there are, in 1 hour, okay, there's 3,600 seconds. There we go. So 3,600 seconds is 60 seconds times 60 minutes in 1 hour, right? So we multiply 2.44 hours by 3,600 seconds, then we'll have those units of time where we can actually substitute it into our equation. 3,600 times 2.44 gives 8,784 seconds. So hopefully you converted that okay. That's the value we need to plug in for t here. So all the rest is substitutions and button pushing. 4 pi squared r is this, 4.38 by 10 to the 6. Remember, sometimes we have to sort of think about, is it the radius of the planet plus some altitude, but they're just giving it to us, you know, the radius of the orbit. So there's no extra like, oh, I got to add in altitude above the surface plus the radius of the planet. You know, we've seen that before. So be prepared to just read the question carefully, and, you know, it might be one extra calculation. Don't forget to cube this number, right? That will drastically change your answer if you lose this, you know, exponent there. G is 6.67 by 10 to the negative 11. And since I took all the time to work through the base units, let me just say that this is in meters cubed per kilogram second squared. So I'm going to put those per kilogram second squared up here. Okay, so G is in the denominator, so meters cubed per kilogram second squared. Those are the base units of G. Okay, and I said, you know, at the very bottom of the whiteboard, I said, note the units of distance is cubed here. and the unit of time is squared. Like, we've seen that. That's what Kepler realized, right? The cube of this is related to the square of that. Those happen to be the base units of G, and by no accident, right? This all works out here. Kind of nice. And then T squared, that's why we did this. So we can plug in 8,784 seconds, and don't forget to square that. Just in terms of the units, the seconds squared cancel, the meters cubed cancel, nice. Kilograms of mass. So it all works out nice for you. But don't forget to, like, I don't want to cross out these seconds squared because I need to square the number too. It's still my calculation. At this point, I'm going to do this. And then let's see here if I do this and this and this. So I've got 4 times pi squared times 4.38 by 10 to the 6th cubed divided by, open parentheses, 6.67 by 10 to the negative 11 equals divided by 8,784 squared equals, and I get a final answer of 6.45. I'm going to say 6.4 by 10 to the 23. So we get a final answer. 6.4 by 10 to the 23 kilograms.